Hello, in this lecture I will talk about mathematical induction. Mathematical induction is a logic method to prove that a statement, a claim or an equation is true for all the natural numbers. A natural number is a positive number that is also an integer, like 1, 2, 3. Actually, we have two steps in mathematical induction. The first step is we check the claim or the equation or the statement for n that equals to 1. That is to say, we check if the claim is true for n that equals to 1. And then if it is true for n equals to 1, we will move to the second step, and in the second step we will assume that the equation or the statement or the claim is true for n, and then we will prove it for n plus 1. So we will assume that the equation is true for n. That is the induction's hypothesis or induction's assumption. And we will rely on that assumption in order to prove the claim for n plus 1. Okay, I will explain the logic behind the mathematical induction. You should remember that we have already proved that the statement or the claim is true for n equals to 1. Then we will prove it, and then we already proved it that if it's true for n, then it must be true for n plus 1. So we have already proved that the statement or the claim is true for n then that equals to 1. And we have already proved that if the claim is true for n, it must be true for n plus 1. So we have already proved that it is true for n that equals to 1. So according to our general proof, it must be true for n plus 1. That is to say, for 1 plus 1, because n equals to 1. So it is true for 2. And then we will make the same process again. So now we know that it is true for 2, n equals to 2. But when we know that it is true for n equals to 2, we also know that that is true for n plus 1. So it is also true for 2 plus 1. It is true also for 3. And when we know that it is true for 3, we also know that it is true for n plus 1, and n equals to 3, so it is true for 3 plus 1, so it is true also for 4, and etc., etc. And in this way, actually, we proved the claim for all the natural numbers. Okay, so that is the logic behind the mathematical induction. Now I will give you two examples in order to clarify the topic. Okay, the first example will be, we want to prove that the equation 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So actually this is the claim of the statement of the equation that we want to prove for all the natural numbers. That is to say, for 1, 2, 3, 4, okay, for all the natural numbers. So the first step that we must to do is to check the claim for n that equals to 1. So we will check if this statement is true for n that equals to 1. Okay, so the first step so if we checked this statement for n that equals to 1, then we actually get that we have in the left side of the equation 1, because n equals to 1, equals to n times n plus 1, so n is 1, 1 times 1 plus 1, all divided by 2. So 1 times 1 plus 1 equals to 1 times 2, all divided by 2, is 2 divided by 2 equals to 1. So 1 equals to 1. So we passed the first step. We checked for n that equals 1 that this statement is true, and indeed it is true for n that equals to 1. Now the second step, in the second step we will assume that this statement is true for n, and then we will rely on that assumption in order to prove this statement or this claim or this equation for n plus 1. Okay, so first of all we will assume that the statement is true for n, so we assume that 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So actually this is the first equation. This is the actually the inductions hypothesis or inductions assumption. So the inductions assumption or induction hypothesis is that this statement or claim is true for n. That is to say 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. And according to this assumption, or according to the inductions hypothesis, we will prove the statement or the claim or the equation for n plus 1. So we will prove this statement for n plus 1. So actually this is so we must prove the second expression, that this statement or claim or equation is true for n plus 1. That is to say, it is true for 1 plus 2 plus 3 plus n plus 1 equals, here in the right side of the equation we will put n plus 1 instead of n, because we want to prove this statement for n plus 1. So wherever it is n, we will put n plus 1 instead of n. So instead of n, we put it here in n plus 1, and instead of n, we put it n plus 1, so it is n plus 1 plus 1, all divided by 2. Okay? Wherever is written in the statement n, we put n plus 1 because we want to prove the statement for n plus 1. Okay, so we assume that expression 1 is true, and we will rely on that assumption in order to prove that expression 2 is true. Okay, so actually we know that expression 1 is true because we assume that it is true. So the left side of the equation equals to the right side of the equation. So actually in the second expression we can substitute this expression by the left side of expression 1 because we assume that expression 1 is true, so we can substitute the left side of the equation in the right side of the equation because we assume that expression 1 is true. Okay, so we will do it now. So we will substitute one side of expression 1 in the other side of expression 1 because we assume that expression 1 is true. So we can write, instead of 1 plus 2 plus 3 plus n, we can write n times n plus 1 all divided by 2, and then the remaining is n plus 1, and we have to prove that it is equal to n plus 1 n plus 2 all divided by 2. So here actually we substituted this expression by this expression because we assume that expression 1 is true, and according to expression 1 this expression equals to this expression, so we can substitute this expression by this expression. So here we have the same expression as in the statement 1, so we can substitute this expression by this expression because according to our assumption they are equal to each other. So we substituted 1 plus 2 plus 3 by the expression of n times n plus 1 divided by 2, because we assume that they are equal to each other. So, and then we have in the second expression n plus 1, so we will not touch on this expression, we will leave it as it is. So we have to prove that in total the left side of the equation is equal to the right side of the equation. Okay, actually we can divide the two sides of the equation by n plus 1, because we can divide it by n plus 1 because n is natural number. It never can be 0. So we can divide it by the two sides of the equation by n plus 1. So after we divide the second expression the two sides of the second expression by n plus 1, we actually got n times n plus 1 divided by 2. When divided, we will divide it by n plus 1. What is left is n divided by 2, and n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by 2 divided by n plus 1 is equals to n plus 2 divided by 2. And we can actually say that n divided by 2 plus 1 equals to n divided by 2 so here actually it is n divided by 2 plus 1, and here we separated n plus 2 to 2 parts. N plus 2 divided by 2 equals to n plus 2 plus 2 plus 2, and actually we got that n divided by 2 plus 1 equals to n divided by 2 plus 1. Okay, it is n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2 is 1, so we got the final result that n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we proved that expression 2 for n plus 1 is true according to our assumption that expression 1 is true. So in this way actually we proved that this statement is true for all the natural numbers, because we have already checked it for n equals that 1, and we found it that this expression is true for n that equals to 1. So because of the fact that we assumed that if it is true for n, it is true for n plus 1, so we can say that we are 100% sure that it is true for n equals to 1, because we checked it, that is true for n equals to 1. So from the fact that it is true for n equals to 1, it is also true for n plus 1, that is 2. And from the fact that it is true for 2, it must be true for n plus 1, that is 2 plus 1, according to our general proof that when it is true for n, it must be true for n plus 1. So if it is true for 2, it must be true for 2 plus 1, that is 3. Then when it is true for 3, it must be true for n plus 1, that is 3 plus 1, because n equals to 3. So it is true also for 4, and etc. etc. And in this way, we actually proved this statement or claim or equation for all the natural numbers. Okay, now I will give you a second example, and we will prove it by mathematical induction. The second example will be so we have this statement that n to the power of 3, that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, and all divided by 4. Okay. So I will repeat the statement that we must prove for every natural number, or for all the natural numbers, is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. So the first step that we have to do is to check this statement for n that equals to 1. So we will check it for n that equals to 1. So we actually checked it for n that equals to 1, and then we found that it is true for n that equals to 1. Because when n equals to 1, in the left side of the equation we have only 1 to the power of 3 that is actually 1 equals to n squared times n plus 1 squared all divided by 4, and n equals to 1, so it is 1 squared times 1, because n equals to 1 plus 1 square all divided by 4. So it is actually 1 square, 1 plus 1 is 2, times 2 square all divided by 4. And 1 square is 1, and 2 to the power of 2 is 4. So it is 1 times 4 divided by 4, or 1 times 4 is 4, and 4 divided by 4 is 1. So 1 is equal to 1. So we passed the first phase, the first step, and we indeed found that this statement is true for n that equals to 1. Now the second step is to assume that this statement or this claim or this equation is true for n. It will be our first expression, and then we will prove that it is also true for n plus 1 according to our assumption that it is true for n, or we will rely on our assumption that it is true for n, and we will prove that it is also true for n plus 1. Okay, so we will start with the second step. We will do the inductions hypothesis. We assume that the statement is true for n. That will be our first expression. So this is actually the inductions hypothesis or inductions assumption. We assume that this statement is true for n, and according to this assumption we will have to prove that it is also true for n plus 1. So we will build our second equation, or our second equation that we have to prove. So we will have to prove date. One to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 to the power of 3 times n plus 1 plus 1 to the power of 2 all divided by 4. So we will have to prove that this statement is true for n plus 1, or 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, because we must to prove this statement for n plus 1. Okay, so in the right side, in the left side of the equation, we have n plus 1 expressions, and in the right side of the equation, wherever we have in the original expression n, we will put n plus 1, because we must prove this statement for n plus 1. So here we have n square, so we will put instead of n square n plus 1 square So instead of n square, we have to put n plus 1 square, and here we have n plus 1, so we will put instead of n plus 1, so it will be n plus 1 plus 1, because now instead of n we substitute n by n plus 1, so it is n plus 1 square, all divided by 4. So we have to prove that the right side of the second expression equals to the left side of the expression. Okay, so we will actually use the same technique in order to prove the second expression. Actually, as you can see here, in the left side of expression 2, the left side, this expression equals to n squared times n plus 1 squared divided by 2. Or you can see here, this expression equals to this expression. It is the same, and we assume that 1 to the power of 3 plus to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 4. So we can substitute this expression by n squared times n plus 1 square divided by 4, because the induction's hypothesis is that expression 1 is true, and if expression 1 is true, 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square divided by 4. So we can substitute 1 to the power of 3 plus 2 to the power of 3 plus n to the power of 3 by n squared times n plus 1 square divided by 4, because we assume that the first expression is true. So we can substitute the left side of expression 1 by right side of expression 1, because we assume that this expression 1 is true. Okay, so we will, in the second expression, we'll substitute 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 by n squared divided by n plus 1 square, all divided by 4. So actually we substituted this expression by n squared times n plus 1 squared divided by 4, because according to the hypothesis, induction's hypothesis, this expression equals to n squared times n plus 1 squared divided by 4, and we assume that expression 1 is true, so we can substitute this expression by n squared times n plus 1 squared divided by 4. And then we have in the second expression n plus 1 to the power of 3. So we will leave it as it is. Okay, and we must prove that the left side of expression 2 equals to the right side. Okay? We can divide the two sides of expression 2 by n plus 1 square. It never can be 0 because n is natural number, so we can divide the two sides of this expression by n plus 1 square. So we will do it now. So here, after we divide the two sides of expression 2 by n square, we got that n plus 1 square divided by 4 plus n plus 1 to the power of 3 divided by n plus 1 square equals to n plus 1, all equals to n plus 1 plus 1 is n plus 2, and we divide all by n plus 1 square, so what we left here is n plus 2 square divided by 4. So we can multiply two sides of the equation by 4, and we will get that n plus 1 square plus so after we multiplied by 4 the two sides of the equation, we got here n plus 1 square plus 4n plus 1 equals to n plus 2 square. So we will open the brackets So we have expression 2. In expression 2, we actually divided both sides of the equation by n plus 1 square, and after the division we got here n square divided by 4, because we divided both sides of the equation by n plus 1 square, and n plus 1 to the power of 3 divided by n plus 1 square is n plus 1, and after we divide this by n plus 1 square, we left with n plus 2 square divided by 4. So we will multiply both sides of the equation by 4. So it will be n square plus 4n plus 4 equals to n plus 2 square. And then we have here n square plus 4n plus 4 equals to n square plus 4 plus 4n, or n square plus 4n plus 4 equals to n square plus 4n plus 4. So actually we assumed that this expression is true for n, and according to this assumption we proved that this statement is true for n plus 1. And in this way we actually proved that this statement is true for all the natural numbers, because we checked for n equals to 1, and after we found that it is true for n equals to 1, then we can deduce from it that it must be true for n plus 1 also, because we have already proved that when it is true for n, it must be true for n plus 1. So we proved by checking that it is true for 1, then it must be true for 2. And when it is true for 2, it must be true for n plus 1, or for 2 plus 1. It must be true for 3, and when it is true for 3, it must be true for 3 plus 1, for 4, and when it is true for 4, it must be true for 4 plus 1. So it is also true for 5. So in this way, we proved that this statement is true for all the natural numbers. Okay, that is exactly what we needed to prove. Okay, thank you very much.